Carbon and its compounds. Carbon is a chemical element that has the symbol C and the atomic number 6. It has 3 isotopes with mass numbers 12, 13 and 14. C14 is radioactive. Elemental carbon exists in nature in crystalline as well as amorphous forms as shown here. In combined forms, carbon is present in the food we eat, the clothes we wear, the cosmetics we use, in fuels and many of the drugs and medicines. Carbon is a special element because it plays a dominant role in the chemistry of life. Bonding in carbon, the covalent bond. Covalent bondings is a form of chemical bonding characterized by the sharing of one or more pairs of electrons between two atoms. Carbon forms compounds mainly by sharing of electrons. The most common type of covalent bond is the single bond, where one pair of electrons is shared between two atoms. Ethane is an example. All bonds with more than one shared pair are called multiple covalent bonds. In a double bond, 2 pairs of electrons are shared.
Ethane
is an example. In a triple bond, 3 pairs of electrons are shared. Ethyne is an example. Melting points and boiling points of some compounds of carbon. The forces of attraction between the molecules of a carbon compound are not very strong, so they have low melting and boiling points. Versatile nature of carbon. Carbon has the unique ability to form covalent bonds with other atoms of carbon, giving rise to large molecules. This property is called catenation. Since carbon has a valency of 4, it is capable of bonding with 4 other atoms of carbon or atoms of other monovalent elements. The bonds that carbon forms with most other elements are very strong, making these compounds exceptionally stable. Saturated and unsaturated carbon compounds. Saturated compounds are compounds in which carbon atoms are joined together by single bonds. Unsaturated compounds are compounds in which carbon atoms are joined together by double or triple bonds. In order to arrive at the structure of simple carbon compounds, the first step is to link the carbon atoms together with a single bond and then use the hydrogen atoms to satisfy the remaining valencies of carbon. Unsaturated carbon compounds are more reactive than the saturated carbon compounds. Affinity of carbons with other elements. Carbon has a great affinity with hydrogen. Carbon also forms bonds with elements such as halogens, oxygen, nitrogen, and sulfur. In a hydrocarbon chain, one or more hydrogen atoms can be replaced by these elements, such that the valency of carbon remains satisfied. In such compounds, the element replacing hydrogen is often referred to as heteroatom. These heteroatoms confer special properties to the compound, regardless of the length and nature of the carbon chain, and hence are called functional groups. Homologous series. A series of organic compounds that have similar structural features but differ from adjacent members by CH2 group is referred to as homologous series. Each member of homologous series is called homologue. Characteristics of homologous series. Observe the schema shown here. Structural formula. All the members of the homologous series have a same structural formula. Molecular formula. Molecular formula of different members of a homologous series differs from previous and next member by CH2. Nature of element. All the members of series have same type of elements. Functional group. All the members of homologous series contain same functional group. General formula. Members of a homologous series can be represented by a general formula. Molecular mass. Molecular mass of any 2 consecutive members differ by 14 units. Chemical properties. All the members of a homologous series have same chemical properties due to same functional group. Methods of preparation. Generally, all the members of a series can be prepared by using same method. Physical properties. Physical properties of the members of a homologous series vary with the increase in atomic weight. Nomenclature of carbon compounds. The names of compounds in a homologous series are based on the name of the basic carbon chain, modified by a prefix or suffix indicating the nature of the functional group. Chemical properties of carbon compounds. Chemical properties of carbon compounds, the four important chemical reactions of carbon are combustion, oxidation, addition, and substitution. Some important carbon compounds, ethanol. Some important properties and reactions of ethanol are outlined here. Read through to understand. Some important carbon compounds, ethanoic acid. Some important properties and reactions of ethanoic acid are outlined here. Read through to understand. Soaps and detergents. Soaps are sodium or potassium salts of fatty acids produced from the hydrolysis of fats in a chemical reaction called saponification. Detergents are primarily surfactants, which could be produced easily from petrochemicals. Surfactants lower the surface tension of water, essentially making it wetter, so that it's less likely to stick to itself and more likely to interact with oil and grease. Detergents are similar to soap, but they are less likely to form films, soap scum, and are not affected by the presence of mineral in water, hard water. Formation of micelles. The organic part of a natural soap is a negatively charged polar molecule. Its hydrophilic carboxylate group interacts with water molecules via ion-dipole interactions and hydrogen bonding. The hydrophobic part of a soap molecule, its long, non-polar hydrocarbon chain, does not interact with water molecules. The hydrocarbon chains are attracted to each other by dispersion forces and cluster together, forming structure called micelles. In these micelles, the carboxylate groups form a negatively charged spherical surface with the hydrocarbon chains inside the sphere. Because they are, soap micelles repel each other and remain dispersed in water because they are negatively charged. Effects of soap in cleaning. Though soaps are excellent cleansers, they do have disadvantages. As salts of weak acids, they are converted by mineral acids into free fatty acids. These fatty acids are less soluble than the sodium or potassium salts and form a precipitate or soap scum. Because of this, soaps are ineffective in acidic water. Also, soaps form insoluble salts in hard water, such as water containing magnesium, calcium, or iron. The insoluble salts form bathtub rings, leave films that reduce hair luster, and roughen textiles after repeated washings. Synthetic detergents, however, may be soluble in both acidic and alkaline solutions and do not form insoluble precipitates in hard water.